Good day and welcome. Thank you for attending the 2021 Virtual International Crosstie and Fastening Systems Symposium. All of us here at Illinois are excited that you have chosen to listen to our recorded presentations. I'm excited today to present to you the effect of traffic type on concrete crosstie ballast pressures using the support condition back calculator. My name is Riley Edwards, and I was fortunate enough to get to work with Camilla Silva. She was a graduate student that has since departed here from Illinois. Camilla was tremendously helpful in the preparation of this conference material, and I've also been assisted by Marcus Dersch. In summary, what we're going to present to you today is the demonstration of a methodology to non-destructively evaluate what the pressure is beneath concrete crossties. What we did is we chose to turn the crosstie itself into an instrument that allows us to check the pressures beneath it at an interface that's incredibly challenging to instrument using other kind of more traditional tactile methodologies. So thanks again for listening. Hope you enjoyed the presentation, and I'll be happy to field any questions after the fact. So what we have today to cover is the problem statement and objective of this project. I'm going to give you a brief review of the back calculator, how it's used, and how it was initially developed. I also want to talk to you about data that we collected at 3 different field sites. I'll summarize each of those as I go throughout today's presentation. Talk about kind of some qualitative support condition analyses that we've done using heat mapping. Then we'll talk about quantitative ballast pressures and how they vary as a function of rail seat load, tonnage, and the pressure within a given train consist. I'll go over some conclusions and then some future work. So the objective of this project was initially to develop a non-intrusive method to quantify support conditions and how they varied over time. We were approached by several different entities that had an interest in prioritizing their surfacing or improving the design of their concrete crossties, and an instrumented crosstie that allowed us to understand what the pressure is beneath it allowed us to address both of those challenges. And specifically in terms of surfacing, we know that surfacing ties up a lot of valuable track capacity, and if we could lengthen these surfacing intervals without it being to the detriment of our tie's health, that would be advantageous to our industry. The challenge, as I said earlier, is inherently difficult to quantify the pressure at this interface without manipulating the experimental conditions by inserting some other form of instrumentation. So our approach was to back calculate the ballast support condition based on measured bending moments collected on the crossties. And much of these data I'll present were actually captured while conducting research aimed at optimization of concrete crosstie designs. So the way that we constructed the 2-dimensional crosstie bending model was to divide the crosstie into 6 bends having equal width. Each of these bends contains a percentage of the total reaction force. You can see them labeled 1 through 6 at the bottom of the screen. There are 9 inputs to the model. 7 of these model inputs are bending moments. 5 of these are captured using surface mounted strain gauges. I'll show you some pictures of these a little bit later. And these surface mounted strain gauges were installed at the location shown in red on the tie below. And we also know that the bending moment at the free end of the crosstie is 0. So we also have 2 0 known bending moments from the end conditions. In addition, we have 2 approximated rail seat loads. I say approximated because we did not instrument the rail seat itself. We used either nearby data from wheel impact load detectors, or we had strain gauges in adjacent cribs at our field sites. We also assumed that the rail seat load was uniformly distributed across the rail seat, and there's been other work that we've done here at Railtech on that subject, but that's its variation across the rail seat is not the subject of today's conversation. To further discuss 2 boundary conditions that were set up, we have force equilibrium. This means that all of our bends should sum to 100%, and the force value for each bend should be positive. We have no negative exchange of forces from the tie to the ballast. So the way that the back calculator works is we define input loads and moments. Then after this, we generate a randomized support condition to describe the possible support that could be there. We determine if those aforementioned boundary conditions are met or not. If they are not met, we discard the support condition and we iterate. One of the ways that we generated the random variables to start our searching of support conditions is through a Pareto distribution. The holistic process we used here for the back calculator was an optimization process known as simulated annealing. And simulated annealing is important because it allows you to at least temporarily accept suboptimal conditions to make sure that you're not in a local minima or maxima. Once the boundary conditions are met, we would compute the moment matrix and we would compare it with known moment matrices to determine if we had a reasonable percent error. And we would get our output resultant support condition. So now I want to take you to our first field site. This site was on Amtrak's Northeast Corridor, double track territory in Edgewood, Maryland. A lot of different operators over that portion of Northeast Corridor. Our instrumentation was installed on track 2, primarily handling northbound traffic, and this traffic included long distance and intercity passenger trains, freight trains, and MARC commuter rail trains. In total, the data that I present today will encompass 2,500 trains or 23,000 axles. Ambient temperatures range from 32 to 90 degrees over this time period. And here's a breakdown of some of the different train consists that we captured and what their loading conditions are. I'll draw your attention to freight locomotives and the loaded freight cars, as well as empty freight cars, because I'll be presenting these data momentarily. So one of the things that the support condition back calculator gives us is the ability to show a balance of forces in graphics similar as the two shown on top. The first one on the left, you can see the distribution of the loads under the freight locomotives, and you can see that a lot of the reaction forces are quite centered underneath the rail seat, beneath the rail seat. On the image of the right, you can see an empty freight car, and you can see similarly the distribution of reaction forces are beneath the rail seat, but we see a much lower magnitude in force. And this was indicative of a location where we had seen very good support, newly tamped track, and the loads being passed generally vertically straight from the rail seat down to rail seat support beneath the tie. One of the things that we did is we looked at a distribution of ballast pressure in comparison with what the ARIMA Manual and Railway Engineering recommends for maximum concrete cross-tie ballast pressure, which is 85 psi. So the vertical line on this graphic depicts the 85 psi limit, or so we could refer to it as, that ARIMA puts forth, and the blue line is the ballast pressure from all the different bends that were shown to you, all the bends across the bottom of the cross tie. If we look at just the rail seat bends, we see that those bends, not surprisingly, based on the data that we looked at a couple of minutes ago, those bends show higher pressures. And we find that approximately 10% of the rail seat bends pressures exceed this value of 85 psi that's put forth in ARIMA. We know that doesn't mean instantaneous fracture and failure of the ballast, but we know that it's important at least to be able to reference to this threshold because it does have some level of engineering validity associated with it in our industry. We can also see that looking at some of the other bends, such as the bends on the end or the center bends shown in the lower left of this graphic, we see that we have very, very low pressures, none of which are exceeding the ARIMA value. So just as a reminder, along the x-axis here, we have ballast pressure in PSI, and along the y-axis, vertically, we have percent exceeding. So this tells us the percentage of the wheel passes in which the ballast pressures were exceeding a certain level. Additionally, we wanted to look at heat mapping by looking at the tie in plan view. And in the case of Amtrak, we had two different timestamps, approximately 6 months apart, showing two different seasons and also two different levels of tonnage that had been accumulated. So for each one of the ties that is shown here, what you can see are two different numbers. These numbers represent the median, the pressures resulting from median rail seat loads across all 6 bends of the crosstie at the 2 different timestamps for each of these given types of rolling stock that were operating on Amtrak, on Amtrak's Northeast Corridor. And we can see graphically once again that the rail seat bends show the highest pressures, and it's interesting to look down and you can see some of the loaded freight cars are the ones that are up to and exceeding the Urbana recommended values, as we talked about earlier. So those are the median rail seat loads. We can also look at the 95th percentile. So only 5% of rail seat loads were exceeding the values that we see on the right. So these 95th percentile rail seat loads generated bottom of crosstie pressures, as shown here on the right-hand side. We have, once again, 2 different quarters. Quarter 3 is shown in the upper right, and quarter 1 is shown in the lower left. And once again, the hotter colors, the more intense the red color, the higher the values. And again, these are even higher by definition than the median rail seat loads, the pressures generated by the median rail seat loads. So we can see very high pressures here in excess of the Urbana recommended value. So once again, lack of center support at this site. We saw the highest values under bends 2 and 5. These are beneath the rail seats, and we didn't see a significant change quarter over quarter after the accumulation of around 12 MGT on the Northeast Corridor. We also looked at ballast pressure within a given train pass, and I like this comparison because it shows you kind of 2 of the bounding load scenarios on the Northeast Corridor. We have an Amfleet train pass on the left, and as you look at the 2 axes on the bottom, we have wheels, and along the length of the crosstie is what the secondary x-axis is, and then we have ballast pressure on the vertical axis. Same for the loaded freight train pass on the right. And we see the significant difference between these 2, the pressures generated beneath the crosstie for these 2 different types of rolling stock. And not surprising, we have obviously significant difference in the wheel loads. But what we find on the loaded freight train passes that we see maximum pressure values in excess of 120 PSI for certain wheels on that given train. Our second site is a light rail transit site. It was installed on Metrolink, the transit agency for the greater St. Louis area. The site happens to be in Fairview Heights, Illinois. It's double track, and we have instrumented the westbound track that sees many LRV passes per day on very tight headways, especially during the rush hours. We found the rail seat loads to be around 4 kips at our site, collected these data back in 2016, and more recently processed them in light of the project that I'm discussing with you today. Quite an uninteresting distribution of rail seat pressures beneath the Metrolink LRT. We have very uniform support conditions at this site with incredibly low pressures. And we can compare this even to the empty freight car, the least demanding load on Amtrak's Northeast Corridor, and we can just see the significant difference between the uniformity of the pressures on Metrolink in St. Louis and on the lightest of cars that are operating on Amtrak's Northeast Corridor, at least in terms of rail seat pressures generated. This is an interesting graphic that shows us the distribution of ballast pressures for both field sites. The Metrolink data that I just showed you from St. Louis are down here, very low pressures and low rail seat loads. The Amtrak data are shown in blue, and we've also thrown on here some predicted pressures based on Eisenman and Talbot, and also drawn on here the ARIMA allowable line once again. So these are real data shown on these lines, significant difference in terms of what's seen on light rail and what we see on Amtrak. This is not surprising, but it also gives very useful insight into ballast life and also the design of the crossties themselves. Another good example of very low ballast pressure values at our second site. This is still St. Louis Metrolink. Here's our 85 PSI value put forth by ARIMA as our maximum allowable ballast pressure, and here's the entirety of our of our bends beneath the cross ties in St. Louis. Nowhere near, plenty of residual excess capacity for at that ballast to cross tie interface. Going back to the plan view, heat maps of the ballast pressure for concrete ties, we've added one more row under the bottom down here. This is our light rail transit vehicle on Metrolink. We see very light colors and very uniform pressure distributions that maps to the data that I just presented earlier. So this means we have a uniform support condition, and you can see very clearly how the two sites differ. Now let's go to our third and final site. This is a heavy axle load freight location on one of our Western Class 1 railroads out in Nebraska. Instrumented one of the two tracks in a double track territory, and it handles primarily loaded coal trains. Here's what the instrumentation looks like. It's been installed quite a few years at this location. We have processed it recently in light of this particular project, and the wheel loadings, thanks to the good health of our wheel sets for most of our unit trains that are in operation, we have a rather consistent wheel loads of 36 kips, and we see most commonly 18 kip, approximately 18 kip rail seat loads at this location. Here's some of the ballast pressure values. This time, instead of the percent exceeding lines being for different bends within the cross tie, this is for 4 different cross ties that were instrumented at this particular field site. What we found is that a few of the ties at this field site exceeded the allowable ballast pressure of 85 psi, but it was relatively low percentages of those. And looking at the plan view, the unique difference between the Amtrak Northeast Corridor site, the St. Louis Metrolink site, and the heavy axle load freight site is the distribution of the ballast beneath the cross tie and how that changes the pressure. At the heavy axle load freight site, we saw more center-bound conditions, and you can see that as shown in a couple of the cells that are highlighted in these four ties down here. So above at Amtrak, we are varying the different types of rolling stock that are operating over the over the field site. In St. Louis, we only have one type of vehicle that's operating over that field site, so it's shown here, and we've looked at it earlier. What we have on the Western Railroad, the Class 1 field site, is we have data from 4 different ties. These ties are very close to one another, and we can see similarities, yet some differences in terms of how the support is distributed among these 4 ties. And we see some exceedances of the ARIMA recommended values. So some conclusions on the Amtrak Northeast Corridor field site: we see a lack of center support. We see if we have rail seat loads in excess of 17 kips, that's when we see the 85 psi allowable ballast pressure value exceeded, and this happened in about 10% of our data. We never saw the center or end pressures exceed the ARIMA threshold at this particular site. Pressures at this location are linearly related to rail seat loads. That's not always the case. There are some non-linearities that we've picked up at other locations. The tonnage didn't seem to change the support condition, and we checked this statistically as well. Metrolink, we see very uniform support. Rail seat load of 4 kips results in pressures that really only get you about 25% of the way to the ARIMA recommended value. So this tells you something about possibly, if you're allowed to manipulate some of the other design conditions, about the potential functionality of a smaller area, bearing area on the bottom of a cross tie for an environment like this. From the heavy axle load freight site, we saw some variability among the ties. Some of these also exceeded ARIMA's recommended value of 85 psi for the pressure at the ballast to tie interface. Future work for this project includes further improvement of the ballast back calculator, so it can be used as a method of ballast pressure measurements, determination of tie health and prediction of cracking, subgrade demand characterization, and better optimization and prioritization of maintenance activities. We also are talking about using strain as a direct input to avoid some of the calibration challenges that you may have with moment conversions and cross-tie geometry. changes with the various designs that we see out in industry today. We also want to develop a deterioration rate model based on the collective pressures and loads from these 3 field sites. Thanks again for the opportunity to present to you today. I hope you enjoyed this. It's an exciting tool that we continue to develop. We're excited to continue to hear your interest as an industry about its functionality and the way that it can be used as a business tool at your own individual railroad. So please feel free to reach out to me. As I said, this work was a really great partnership between myself, Camilla, and Marcus Dersch. We thank the New Rail Center for funding this work, and we also thank the Federal Railroad Administration and the Federal Transit Administration for funding some of the earlier instrumentation that was installed in the field. Thank you again, and have a wonderful day, and enjoy the rest of our virtual event, and we hope to see you in person soon.